evaluated logic-based smart contracts for blockchain systems, so kind of trying to combine the notion of smart contracts on blockchain systems with rule-based or logic-based approaches. And of course, I have to thank Guido here and Regis, and also my supervisor, Giovanni Sartor. First, maybe a small show of hands, like how many of you are familiar with blockchain technology basics or not? Good. So I will not go too much into it, but a little bit, and then yeah, if there's unclear things afterwards, we can maybe discuss it over lunch or during Q&A, because if I would go too much into the details, then it would just take a long time. So yeah, first we kind of looked basically at blockchain systems, how we could combine this with logic-based approaches, and what the utility of this could be, and then we also met some challenges due to the particularities, especially of public blockchains. And finally, which is not in the paper, but which I would like to show to you today a little bit, is some kind of new work that me and a friend came upon after the paper was already done, which could help us to actually implement this using logic-based approaches in a better way. So the basic problem then is that, for example, right now, yeah, mostly the smart contracts on blockchains, blockchain platforms are written in procedural languages, and this is of course quite nice, though even this has its challenges due to the constraints of the system. And then yeah, if you followed the news about this, for example, recently there have been quite some issues with like money getting lost or, well, kind of hacked in a way, and then obviously we want to try to avoid it. We want to try to avoid this, and one idea would be that logic-based approaches can help with that. So, and this also shows that well, they can be very useful, but complex smart contracts that still are secure are kind of hard to do. And yeah, then maybe logic-based smart contracts can be a solution, though. And then the primary challenge we identified is that especially if you have more complex rule engines, then these still have to be either really small or at least have to be in a way cheap to execute, because all the public blockchains rely on the system of using game theory and economics to work. So then you actually pay for the execution, and obviously you don't want to pay too much just because you have a nice rule engine that is maybe, I don't know, 1,000 lines of code or something. So basically, just quickly about blockchain systems. So it's a network of computing nodes where you have a common data structure, the blockchain, and this in Bitcoin, for example, represents a ledger, and also in the other systems with smart contracts represents the ledger for the economic properties. Then there's the goal is always to have consensus about this data structure, and each full node and each time has all the data. And then within the same network, the same rules apply for all the clients, like such as regarding the network transactions and the economics. It's also transaction-based. This is obviously obvious if you have just the ledger data and like a balance sheet, for example, where you add money and remove money, for example. But this still applies even if you have more complex smart contracts that say don't directly deal with money, but try to codify legal relations or other assets like licensing rights or something. It's still the transactions to change the state of the database are always transaction-based, and that's also important to keep in mind. As I already said, transactions are costly, but I will not go into the details of the transaction. What might be important later on is that for all this verification and the structure of the data structure, Merkle hash trees or binary trees are a very important data structure that might be familiar to some of you. Yeah, here you, for example, just to go over this, you see like such a data structure. So this is one block, and then within a block you have like this hash tree structure that is used that the verification and all the data does not take up too much space, and then is condensed into the Merkle root, as it's called, which is then which makes it much easier to verify data quickly without looking at all the rest. So then, when we look to smart contracts, the logic-based smart contracts, there's obviously a lot of prior work. The concept was first introduced by Nick Szabo in the 90s, though more in a theoretical way. And at this point, there was not really a workable implementation. And also with Bitcoin and this kind of public money system and consensus between machines about this system was not really available, so there was not really a working system. And the idea is that they're, in a way, the smart contracts are in a way secure, decentralized, and fair in a way, as you are not supposed to be able to cheat because of the rules written down in the code. Then between the node, there's communication of agreement, and to some degree enforcement of the common rules of agreement and monitoring of the rules written down. So this allows for like complex codification of legal relations. Presently, the codification is done in bytecode, in a procedural language that is compiled to bytecode. And like here, for example, like I mentioned here, Solidity or Serpent are two procedural languages that are somewhat similar to JavaScript, C, and Python, and that then provide explicit instructions for this codification. And then in our paper, to come back to that, we designed, we worked with an example contract where it was the licensing contract. So here you see the pseudo, well, it's not actual legal, it's not an actual legal license, which would obviously be even longer. But so here we have a licensor that grants a license to evaluate a product. Then the licensee is not allowed to publish the results of the evaluation without approval. And yes, if the licensee does not adhere to the conditions, then the license will terminate automatically. And so this was still reasonably complex and actual use case, but we could also, in the space of the paper, still evaluate it into how it could be used in a logic implementation. We also, to ease like our transition from the legal text to the logic rules, we used the state machine as help, and there we were inspired by the work of Professor Goodenough, as I think at least in such cases where it's doable, it's quite helpful to evaluate like actually what the potential states of the license contract are and like how they affect each other, and this can help to then draft the logic rules. And this is then our example of the logic-based model. I didn't get it quite as nice on the slides as it's in the paper, but if you want to see it with nicer formatting, you can look at it in the paper. And then, yeah, this is basically based on deontic defeasible logic and this contract logic implementation and implemented and evaluated with Spindle, which I think Guido is also very familiar with. And then assuming you have a good logic engine implementation and the rules and boundaries are much clearer than in a purely procedural example, and the idea is also that, well, assuming there are no, like I said, a good implementation, then that it's not possible to cheat or something like that. Then we looked at the utility of logic-based smart contracts and kind of looked at compared it to the normal stages of a contract lifecycle, where you have like formation and negotiation, contract storage and notarizing, enforcement and monitoring, modification and dispute resolution. And there we compared several approaches, where you have the on-chain approach, off-chain approach, and a kind of on-off-chain approach. And what this means is, if you, because of the cost associated with running smart contracts, we evaluated whether either it's feasible to run all the rule engine code on the blockchain, whether it's possible to run some code or all of the code off the chain and then somehow get it, have it talk back to the chain and just codify the result on the chain, or some combination of those. And then for the formation and negotiation, well, that's easily to do on the chain, but depending on if you want, for example, natural language text to go with it, obviously you could also do it first off-chain and then like manually and then codify it on the chain. But then you have the actual legal relation from a legal point of view would actually take place before, and then you just kind of notarize it or store it if you want on the blockchain, and then you just use the blockchain kind of as a monitoring tool for the consequences. And yeah, also for the modification and dispute resolution, there's different approaches. For example, either you can have like a kind of hub and spoke model where the contract is divided into different parts, and if you update a part, you just update the address that's stored on the chain. And yeah, also with dispute resolution, there's different approaches depending on how you implement it. Like, for example, if you would try to incorporate a knowledge base that's taken into account by the rule engine, then this would make modification and maybe also dispute resolution easier. Then there are, on the one hand, let's say the logic-based approaches, and then there are the more blockchain-based approaches where that take much more into account the economic incentives and game theory, so that, for example, which I will show an example of later, where, for example, to get people to cooperate, they would just have to post a bond, for example, and then if they are found not to cooperate, then they would lose the deposit. Yeah, I talked mostly about this already. So we evaluated some additional possibilities, such as equation-based approaches or neurosymbolic systems for on-off-chain approaches, though I have to admit that my co-authors actually know more about this than me, so maybe we can discuss this later. And then coming back to our main finding about the costs of different approaches, we constructed a very basic inference mechanism, and then used a procedural, defeasible logic and equation-based approach, and then compared the costs of the different approaches. And as you see, the procedural approach is quite small, and the equation-based approach as well, but the defeasible logic approach is quite large. If this is like in some amount of Ether on the Ethereum blockchain in this case, and yeah, so as it's like I think by a factor of 10 at least more expensive, or no, not quite, but almost, then yeah, obviously you wouldn't really want to use this, but there might be solutions. How much time do you still have?
10 minutes.
Good.
Including questions.
Sure. Just very quickly, because after we had already finished most of the things, I discussed this also with other people that I know that are working with blockchain technology, and they were working on something very interesting called TrueBit, which I think we could also use to actually provide a much better implementation of this rule engine in a off-chain or on-off-chain approach, so that would be comparably cheap. And it's
How do you spell TrueBit?
TrueBit.
TrueBit? Thank you.
Yeah, basically it allows for a lot of different computation of complex tasks, and is especially adequate for transaction-based databases, and takes into account also the economic properties of and consensus properties of the blockchain. Here you can see like the different people that worked on it. So I talked about with Christian Reitwiesner, and he worked together with these other people. So basically the task giver in a way publishes the question, then the solver provides solutions in a commit reveal manner, and then disputes are resolved using a kind of verification game, which then takes into account the economic properties. And the task giver provides a fee when the solvers provide a deposit and get rewards, and the deposit is then slashed if a cheater is detected. Due to these incentives, the verification game will only be played in case of an attack. An attack basically means that there's a different result from a pool of solvers. Then, as the deposit would be slashed if there's even one cheater, then an attack is only successful if all attackers join forces. So even one honest actor can prevent any attack. So actors agree on a program to run. In our case, this would be a rule engine for defeasible logic or something else. Then this is first run natively to find a solution. And if there's disagreement, then the verification game starts. The solvers rerun the input on an implementation which generates can generate Merkle roots at any step. This is more or less part of the hash tree I showed before. And then you basically get the hash of the first match, and the first step is as a match, and the last step is a mismatch. And then a binary search is done until there's a single step from match to mismatch. And then there's Merkle proof for this step, and then only this one single step has to be evaluated on the blockchain, and this makes it much cheaper than evaluating the whole logic structure on the blockchain. And as for applications, I mean, basically it can work for anything that can somehow be broken into steps, and there's someone else did a similar idea, but this is a little bit different, which is called the Ethereum computation market. And in this case, tasks have to be implemented in Solidity or another on-chain language, and off-chain. But it's supposed to get much easier because they're working on a very lightweight virtual machine. so that the mechanism could work without any code changes and run off-chain and on-chain with the same code. And yeah, what makes it also very interesting for smart contracts is Swarm and other types of these file systems are basically very large distributed file systems that also rely on this hash tree structures a lot. So and they can use this. They then could be directly used more or less as a file system for smart contracts if these tree structures are possible to process in this way. And the good thing is that if everybody agrees, there's almost no strain on the blockchain, on the computation. And if there's disagreement, a cheater is found very quickly. And yeah, I already said the last part. So coming back to our work and our conclusion. So logic-based smart contracts could definitely help usability, provide easy integration into the contract lifecycle. Of course, as a lawyer, I would always say it depends, but that also depends on the specific use case. And if you would provide, for example, natural language implementation as well or not, then I, for example, like the idea that the TrueBit people are pursuing, and I would think into using this for logic-based approaches, but it doesn't exist yet. And exactly as I said, the direct on-chain work proved very costly and hard. And so the TrueBit would also be also a very cost-effective solution. Thanks.
Seems to me one shouldn't be too obsessed with doing worse than procedural code, because procedural code is easy to have fun. I think one of the biggest advantages of the logic-based approach is people get understanding the human verification that the agreement is correctly reflecting intention, and avoid the need for dispute resolution because of the more reliable and consensual in that way. Also, there are a lot of other potential implementation platforms than, Spindle.
Yeah,
So,
sure.
I mean, for example, modal diffeasible logic can be more or less represented in Ergo, which has some very efficient infrastructure that's been, reflects decades of work by people on tabling and logic programming community, for example. So it's quite possible that logic, when run a real agreements that has some complexity to it, would be faster than procedural code because of that. Because it's faster to use a mechanism that's optimized for that type of reasoning than it is when people try to hack it up themselves in procedural language.
Yeah.
Okay.
Yeah, sure.
So yeah, it's not a problem of speed.
Yeah.
It's not speed.
Okay.
The problem is in the experiment, what we did it was just modus ponens. In size B, and then if you just implement tabling, just doing a reduction in programming and similar, it explodes. You use too much resources, you have to pay too much. So it's not really doable. And again, it doesn't really depend.
I'm just puzzled. Cycles are so cheap these days in cloud.
No. The problem is it's in solidity. It's you have the concept which is called gas, which is essentially how much you have to pay for a particular transaction, for a particular type of computation. And then if you just do anything which is kind of logic-based, it explodes.
I guess I'm just, why is this going to persist as a characteristic given how cheap cloud?
Well, again, it's inside the virtual machine. It's not. It's inside the virtual machine.
Is it that it's having to be run
Yeah, it's like, I'm sorry, maybe I should have included that as well, but in Bitcoin you have you have a certain minimal transaction fee for one transaction that you want to run. I transfer you like 5 coins or something. And then in Ethereum, because it has these smart contracts that have actual procedural instructions, then for abuse prevention and kind of also to give a reward to the miners, which provide the nodes of the network, for each transaction and each storage, more or less, there's a certain fee associated, which is the gas, as Guido said. And then there might be possibilities that you implement one big rule engine, and then if you just put the logic rules in another, I would just call this rule engine with this logic rules, then it might be cheaper, but maybe also not, because still the execution, even if you don't have to create a new instance of the smart contract, you still have to pay for the execution that happens.
There's something that just totally doesn't make sense to me here, which is the whole idea of blockchain and distributed ledger is largely to reduce transaction costs in the system. So
yeah, but it still has that.
That are running close to the blockchain infrastructure.
Well, it's in a way
priced so incredibly high that it
high is relative, of course. I mean, it's still probably comparably cheap now, but also the price is always adjusting. So it's in dollar terms, it's hard to say how much it will be, but in Ethereum, for example, the currency is called gas or ether, and then in these terms, it's comparably a lot. So of course, the compared to the dollar price, it always changes, but comparably, say for example to credit card transactions, or if I go to the wrong bank in Germany and draw money, the transaction fees are quite low. But if you are working towards using this for like a business where you have like thousands of transactions, it will add up. So yeah.
Yeah, well, the issue is that essentially you want to have blockchain is just a database. It's just a plain database. What you want to do is to supplement the databases with a twin-function machine, with a twin-function language. If you have a twin-function language, you can have discrimination. So essentially what you do, they've done, they introduce the notion of cost per transaction. So essentially you prevent infinite computations, because if you have an infinite computation, you need an infinite quantity of gas to spend. And then each type of computation has a cost associated to it. And at this point,
that's useful information, but I think it does not really shed light on why we have to worry, why one ought to have to worry so much about this kind of stuff. It seems to me this is a sign of the immaturity of the infrastructure.
Yes. Yes, exactly.
The transaction, that you have to worry about computational costs so much within the context of these transactions. I understand they want to incent people to having some kind of price, but I still stand by what I said before.
Well, our point it means with the current infrastructure provided by Ethereum or other blockchain framework, it's not doable.
Or, well, it's very expensive.
Yeah, actually, it's too expensive.
So the idea is do as much as possible off-chain, and then just verify using the protocol such as TrueBit. Is that the idea?
Well, that was not included in the paper. That is like we evaluated different approaches, but I think one off-chain approach could be TrueBit, for example. Yeah.
But the problem, if you go off-chain, you somehow defeat the idea of the blockchain. That is, of course, we have to find the right balance.
Yeah.
Well, now we don't have
If it's tied closely enough, maybe it'll be.
And I think that's why TrueBit is interesting, because otherwise if you have, other people also know more about this, if you have certain equation-based approaches, sure, it reduces somehow the task also a lot, but also, at least for me, it doesn't make it easier. But that's maybe just me. Yeah.
There's also another issue that many different blockchains now available.
Yeah, sure.
The question in these smart contract scenarios is that you want to make
Yeah, I mean, but there's also, I mean, there's not that many relevant ones, I would say. The biggest ones are right now Bitcoin and Ethereum, if you go by market volume and activity. And then others, for example, have their own currency, for example, but for the actual procedural implementation or the Turing complete machine, the virtual machine, they just basically forked Ethereum's virtual machine. So the same would probably be true for that. There's also people working on private blockchains or things like that, but then why would you not just use a database or something, you know? So.
Well, there is the Ledger initiative by the Linux Foundation. So
Yeah.
Again, I haven't kept track of over 1 month, but it wasn't available. Well, there wasn't anything available yet.
Yeah. I mean, there's definitely a lot of initiatives that could get interesting, but so far, yeah, that's it.
So this idea of having contracts run and be executed in the cloud also was pursued in the later 90s and the kind of earlier mid-2000s by people working on micropayments.
Yeah.
So there's a lot of
Yeah, I think that's.
that the public key infrastructure and other kind of secure protocols would support kind of more particular types of contractual provisions being enforced in conjunction with micropayment and supporting, auditability, dispute resolution,
Yeah.
et cetera, et cetera.
Yeah, I think that's definitely where it's coming from, though I didn't have time to go through all this literature, and we didn't do it in the paper either, because it's in a way important, but not important to show what we wanted to do, I think. Micropayments are definitely, even with the transaction costs, micropayments are still much more feasible with this than with credit cards, for example. Like there's people working on, for example, you can also do something called a micropayment channel, where you just kind of open in a temporary transaction that only gets closed at a later date, and then so you bind a certain amount of money, like $5, for example, and then you deduct, I don't know, 5 cents or whatever every time there's a microtransaction, and so then you can do this very efficiently with this technology, for example, without, yeah.
Okay, let's thank the speaker.